Okay, it's I mean, it's great to have Alessio Figalli over here. I don't think he needs an introduction, but you know, I need to give one. So he got a PhD lightning quick in 2007 under the supervision of Luigi Ambrosio and Cédric Villani at both Scuola Normale Superiore di Pisa and École Normale Supérieure de Lyon. So he was a researcher briefly in Nice and then became almost immediately professor at the École Polytechnique. And then he moved for a good chunk of years at the University of Texas, Austin. And finally, he was appointed professor at the ETH Zurich, where he is also the director of the Forschungsinstitut für Mathematik. He's gotten a number of prizes. I'm just going to actually select the one that he selects himself in the CV. The prize of the European Mathematical Society, Stampacchia Medal, Beltrinelli Prize, and of course, as everybody knows, the 2018 Fields Medal. So he's an expert in PDEs. He's made profound, impactful contributions to Morse transport, regularity for Mongian pair, free boundary problems, Stefan problem, random matrices. I've actually left out maybe the very first area in which he worked, which is quantitative stability in geometric and functional inequalities, because that is actually the topic of the 3 Morse lectures.
So, thank you, Camillo, and thanks a lot for mathematics for inviting me here to give these Morse lectures that on the sequence of my sabbatical year at the Institute. So in these 3 lectures, I will try to kind of give an overview of a very broad topic, and I will kind of just select few sub-problems as guiding principle and examples for this meta question, which is stability inequalities. So let me try to make it start a bit abstract, and then with examples we'll delve into more concrete and tools and techniques. But the setup is the following. So what is an inequality? Usually you have some space, X. It could be a functional space, so a space of functions. So usually these are infinite dimensional, a space of sets, some objects, and you have some, let's say, function defined on it. So I have some function f that takes real values. Let's say, since I want to minimize, I'm going to assume directly that these are non-negative values. And the idea is that I want to find a minimum. Okay, so first step, find minimum of f. And let's say either, so we'll see sometimes you can prove how this minima, so you can characterize the minima by different techniques. But let's say these minima, you can find them in some way. And this is the first step, and I will denote them by calligraphic f. So M denotes the set of minima, and let's say up to shift the value of f, I can assume that the minimum, sorry, this calligraphic f has minimum at 0. Right? Otherwise, I would just change the constant. And I'm going to assume that this is non-empty. Otherwise, let's say what I'm trying to do doesn't make too much sense. So I have a function, and I have some minimizers, which exist. And once you have this set, the real question that I want to understand, so the goal, is how does f look near its minimal value, which is 0 now. More precisely, what I would like to get is that, so more precisely, can I say that if f at some point, at some element little x is very small, then my element x, in some sense, the distance between x and this space of minimizers should be very small. Okay, so this is the stability question. You want to say that whenever you're, so you know f is non-negative, and it takes values at 0, and you want to say that if f is very small, then in reality your point x should be close to the 0 set. Of course, it cannot be true in general without assumptions, but we want to understand in relevant situation whether this is true. So the basic, I will start with example, just a picture. I mean, my f could be in one dimension, something like this. So we'll take some values here. So my question would be, I have to look at the points where f is small. So it means what? It means that I will take a threshold, epsilon, and I want to look at the sub-level sets of f with epsilon very small. So if I'm in a picture like this, it will be like studying f here, here, and here. Or in higher dimension could be a connected set or whatever. But of course, my f could also be like this at infinity, which means that I could have also sets which are not close to minimizers, but just very far away. So this is a situation that most of the case we want to rule out. In particular, we don't do this, but cannot. And to do actually better here, I don't want only to say that if this is small, this is small. I would like even to say something a bit more quantitative. So actually, we are interested in quantitative estimates. So in that, let me try to make a second example, which would be the following. So I'm in a REN now, nice finite dimensional space. I have my f again, which is a function in a REN now. And let's say that the minimum of f, so the manifold M, consists of a single point, 0, for simplicity. So the origin is my only minimizer. Okay. So if f is of class C2, so I have enough regularity. So you see, your f is not negative, and it is 0 at the origin, so it will have 0 gradient. I can perform a Taylor expansion. So, and let me use f is a Morse function, because these are the Morse lectures, so I should mention Morse at least once. Which means that the Echelon of f at 0 has to be now strictly positive, because it's not negative definite, so it has to be positive. Then this means that f of x is by Taylor expansion 1/2 Echelon of f at 0 applied to x plus little of x squared, which means, so near the origin, this is the dominant term, and it's positive definite. So this means that for x close to the origin, I have that f of x will be larger than a constant times x squared, where the constant is positive. And so this means that near the origin, you see f of x, if f is less than epsilon, then x is bounded by constant square root of epsilon. So we have a sort of quantitative estimate of this form. Okay, that by the smallness of f controls the closeness to the minimizer with a square root behavior. So, and you see, this is the best I can hope for. So for instance, if instead f is not Morse, which means that there exists, let's say, some vector on the sphere such that the Echelon is 0, so I have some 0 eigenvalue, then I will not have a bound of this form, for sure. The best I can hope is to jump to the fourth order derivatives. So if the second vanish, the third have to vanish because it's not negative, so I have to jump to the fourth. And this will imply, so at best, I will have that f of x close to the origin will be like x to the fourth at best. So if this would be true if the fourth order derivative are not in these directions are not 0. And so I will have something like f of x less or equal than epsilon implies that x is bounded by constant epsilon to the 1/4. So this is a worse behavior, of course, for epsilon small. So you see, the square root behavior is the best you can hope for. And then otherwise you jump to other powers, which in general will be smaller than square root. So, of course, it is very finite dimensional, and I'm interested in infinite dimensional phenomena, so this doesn't make sense. But before moving to that, let me make also another remark. That if instead f is not C2, say I have the function f of x in a Rn equal modulus of x, singular path. Right, so this is my f. Then you see that f less or equal than epsilon implies, so f of x less than epsilon implies x less than epsilon, which is better. So in some sense, the square root behavior is the best you can hope for when you have smooth functions. When your function is singular, you can actually expect to have even better stability. So here, in some sense, smoothness and stability fight with each other. Okay. But anyhow, in most cases, the function that we end up studying have some smoothness behavior, and it's very rare to find this behavior. There are examples, but it's rare. Most of the time, it's more like this. So all this is to just introduce the step. Of course, first of all, this analysis is very finite dimensional, just this kind of computations, and also is very is based on the fact that I am on a Rn, so a vector space. You know, I can do computation in this, and usually the space of function we study will sometimes not even be vector spaces. But I think it's a good motivating principle, and also it kind of explains some of the phenomena that we observe. So this was just to explain the setup. So the goal of the lecture will be kind of analyze very concrete cases of inequalities and try to understand whether for these inequalities we can produce something like this. So the first example that I want to focus on is the isoperimetric. Inequality. In a red, Euclidean isoperimetric inequality. So what is that? Let's say, let me maybe state it first. So this is the theorem. So the isoperimetric inequality, there have been works already in the 19th century, but let's say if you want it in full generality in a Ren, it's actually not, so it's from the middle of last century, and the full proof was done by Di Giorgi in 58. And it says the following. Let's say I will just focus now on smooth sets. So if E is a subset of a Ren, bounded and smooth, then its perimeter, it means I have my set E, and the perimeter is the area. So it's just the surface area or the whatever n-1 dimensional area of the boundary. So the perimeter controls the volume, and the inequality is that it controls with constant n, volume of B1 to the 1 over n, and volume of E to the n-1 over n. And you have equality if and only if E is a ball. Okay. So Now I want to put this inequality in my setup, as I did, let's say before. But actually, before doing that, let me make a remark. So the isoperimetric inequality. So isoperimetric inequality is scale invariant. So what I mean is that you can, of course, dilate your set, and this term will dilate. So if you dilate by factor lambda, this will scale with lambda to the n minus 1 times the perimeter of E, and the volume will scale with lambda to the n times the volume of E. And so because of this power n minus 1 over n, the lambda will cancel out. So you can always dilate your set. The inequality but doesn't change up to a multiplicative factor. So in some sense, the volume doesn't play too much of a role. So what I mean by this is that if you want to understand this inequality, you can always restrict yourself to sets of fixed volume. So because of this, so without loss of generality, one can assume that the volume of E is equal to a constant, and let's say, let me normalize it to be the same as the volume of the unit ball. Okay, so I just consider sets which have fixed volume like the unit ball. Then if I just fix on this, then my inequality becomes that the perimeter of E is greater or equal than n times the perimeter of B1, because here you get B1 1 over n, B1 n minus 1 over n, which is the same as the perimeter of the unit ball. And equality if and only if E is a ball, but the balls of radius 1, these are just B1 of x, where x is. So you have equality only for unit balls. So the only freedom you have is the translation. Okay, so my setup will be the following now. X denote the space of smooth bounded sets of volume equal to B1, to the volume B1. And my F from X into 0 infinity is just, so F of a set E is the perimeter of E minus the perimeter of the unit. This is okay. And now what we want to do is to understand whether F small implies that E is close to. So the question in this setup becomes F of E very small implies E close in some sense to some ball, unit ball. And again, better if quantitative. So in this kind of setup of the supermetric inequalities, there is a very sharp behavior in whether you are in dimension 2 or in dimension 3 and higher. So here, n equal 2 is very special. So in some sense, I will not consider it too much. I will do everything. I want a result which is true in every dimension. It's very special for a simple reason. So the basic principle which is true only in dimension 2 is the following. Because if you have a set, any set, let's say something like this, for instance, this is your E, or it could be more complicated. What you can always do is to convexify it. So this would be the convex hull. Okay, so you take the smallest convex set that contains it, and in dimension 2, the perimeter decreases under this operation. For n equal 2. And this simple property helps a lot. in this kind of inequalities. You have a procedure to decrease the perimeter and makes the set much nicer. So it's a bit of a miracle, let's say, of 2 dimensions. So it's a sense it kind of hides the real challenges of higher dimensional spaces. So I will mention the result of 3D, but I say you should always keep in mind at least 3D setting.
But is it very special just in terms of how you prove it, or actually the results are qualitatively different?
Yeah, you will see in a second. So there is a theorem which is much stronger in 2 dimension. So in some sense, yeah, you see there are 2 things. Actually, okay, let me do the next example and then. So if you're in dimension n greater than equal than 3, I can produce this example which will fail in dimension 2, which is the following. You take a ball, so the 3-dimensional ball, you take a small circle on the 2-dimensional sphere, and to it you attach a very long and tiny tentacle. Okay. Let's say that the length of this tentacle is capital L, and this is a circle of length epsilon. And then, so you essentially your set is like a sphere with a cylinder on top of it. And now, what is the perimeter here? So the perimeter of the new set, so the perimeter of my new set is essentially the perimeter of V1. So I removed from here a small circle, more or less, but I can attach it back here, right? When I do. Here I don't pay anything, I just move it there. And then I add this tentacle. So this is like a cylinder, which is, so the length here is epsilon, the length here, the length is L, so the surface area is epsilon times L. And so you see that, so the perimeter of this set, and okay, this maybe will have a bit more volume. The volume of this set will be what? Will be the volume of V1 plus the volume of the cylinder, which will be L times epsilon square, because this area, if this is epsilon, the volume here is like epsilon square. So the volume of this cylinder is epsilon square, plus higher order terms, maybe corrections of cubic order. So this means the following, that I can dilate it back just to match the volume. So here, I assume that the volume was the same. So maybe you can just rescale it back, but the correction you see is of quadratic order epsilon. And so if you just now dilate it back, maybe let me do it somewhere else. Here. So if I now I define E prime to be lambda E, where lambda has to have now volume V1, so it would be 1 over volume of V1, sorry, V1 over volume V1 plus L epsilon square, essentially, the 1 over n, which is roughly 1 plus O of epsilon square n. Then the perimeter of E prime will be the same. So it will be still P of V1 plus epsilon L plus the O of epsilon squared. So this means what? That they can find a set which has volume like V1, its perimeter, it's close to V1 by epsilon times L. And I can choose, so now I can choose epsilon much smaller than 1 over L to make this number as small as I want, and this would be even more smaller. And you see that the f of E prime then it will be small. So I can build these examples, right, which have perimeter as close as I want to the ball, but they are not close in a, let's say, L-infinity sense. So they can have points which are very far away. And of course, the number of these tentacles here I drew 1, but I could keep adding them with, let's say, this would be epsilon 1, epsilon 2, epsilon 3, and I could do an infinite sum of them if I make the base the value of this epsilon I very, very small. So this means that my set could be close, could have perimeter very close to the ball, but have infinitely countably many tentacles coming out with very small base. Okay, this example you cannot do it in dimension 2, because in dimension 2, even one single tentacle will pay L. There is no epsilon to L in here. The length of this is just L. So I don't have the possibility to go out with a tentacle in dimension 2. Just space the length of the boundary. So this is the big difference, of course, which means that also the kind of theorems we can try to prove are not really the same. Yeah. So maybe let me. So let me set up the problem I would like to solve. So I told you I want a stability result. I want to say that if F is small, I'm close to be a ball. So I want to now define it properly. So I'm going to define a distance. So definition. Given E and F in my space capital X, I define the distance between E and F to be just you take the indicator functions of the two sets, and you compute the L1 norm, which is the same as computing the volume of the symmetric difference between the two sets. So it means that I have my set E here, I have my set F here, and what I'm going to do is to compute the volume of this area. This is the symmetric difference. So this is my volume, maybe up to constant factor 2. Now that I can float it. No, we finished it. Yeah. So this is my distance between my two sets. And now what I'm going to define is the distance between E and my set minimizers, as you will do in a metric space. It's just the infimum over X in Rn of the distance between E and the ball being 1x. So you take the minimum of the distance between all possible minimizers. Okay. And now my main question is the following. Do there exist some constant Cn, some exponent alpha of n positive, such that the distance between E and the space of minimizers is bounded by Cn times the energy f of E to the alpha of n. Okay. So notice that here I'm looking for a global inequality. So before, when I did these finite dimensional cases, I was saying, oh, let me assume that my function is positive second derivative, then nearby I will have a square root behavior. But of course, this analysis didn't tell me anything about what was happening at infinity. Right? Maybe what my F would have is. Here I'm looking directly for a global inequality. So it should be true for every E, which means that this cannot happen at infinity. So if I go far away, the energy still tells me that I have to be close. Okay? So in particular, if this is true, this cannot happen. I cannot have this behavior. Yes?
Instead of taking that infimum, you required the ball to be around the center of mass of the set. Would that change the picture?
A posteriori, no, it doesn't. So now you take an infimum. Actually, this is a minimum. That's not difficult to prove, because it makes no sense to put the X go to infinity. So just by compactness, you can prove that X lives in a bounded set, and then it has to be a minimum. But then you could also say, okay, why don't I choose already X to be the barycenter? So I match the barycenters of the two sets. A posteriori, it works. But let's say it's more convenient to have the freedom not to worry at the beginning about that. But actually, you will see the barycenter appears in some intermediate steps. So this is the question. So the question, there are two parameters here, the exponent and the constant. And we will come back to both of them. So if you want to prove this, first thing you want to do is probably to start to make some conjectures. What you want to prove? So what should be a reasonable exponent? So what, okay, the constant, maybe you can worry less for the moment. Let's say it will be some large constant, but what about the alpha? So you can just do this computation in the plane. You start from the unit ball, and then you take as a competitor E an ellipsoid, for instance. So E would be an ellipsoid of axis 1 plus epsilon and 1 over 1 plus epsilon, say the semi-axis. So this would be my E epsilon. And then one can do Taylor expansions for every term. So F of E epsilon. So we don't do this now, but I will do something a bit more general in a second. But you do the computation and you can prove that this goes like epsilon squared. And instead, if you look at the distance between E epsilon and M, which is the same as the symmetric difference now between E epsilon and V1. So it's this volume. Is the part which is not important. This goes like epsilon. So in this example, this term goes like epsilon, and this term goes like epsilon squared. So epsilon less or equal than Cn epsilon squared to the alpha n implies alpha of n less or equal than 1 half. So I have this upper bound as a necessary condition. If this inequality is true, it cannot be true unless alpha n is less or equal to 1. Okay. So if it's true, this is like, if this is true, then. So you see, this is the 1/2 that we discussed in the case of the Morse function of the parabola case, right? F of x, which was like x squared at the origin. Then that's what you get, the 1/2. Here I'm telling you the 1/2 is an upper bound. You cannot do better than that. And I think so. The 1/2 actually has been conjectured for a very long time to be the right one. In fact, if you are at n equal 2, this was proven by Bonnesen in 1924. So he proved actually a stronger result. He proved that if you're in the plane, you can find your two. So given a set E, well, it could be more weird than that. You can find. He had some properties about consent, and this, let's say the boundary is connected. You can find a connected and a concentric circle inscribed that concentric circle inscribed and circumscribed R1 and R2, such that R2 minus R1 square is bounded by, I think, L square over 4 pi minus A, something like that, which is the sharp isoperimetric inequality in the plane. So it proved that essentially if this is 0, you are a circle, and if it's small, then in fact these two radii have to be very small. So there was already some result in the stability already back in the 1920s. Actually, there were even previous results at the beginning of the 20th century, but they were all limited mostly to 2 dimensions, because 2 dimensions you can play with, you know, properties of 2-dimensional sets. Instead, we would like to understand the 3-dimensional case. For the three-dimensional case, I'll say for many years there were not strong results, in many partial results, but one which I think is worth to explain, at least for these lectures, is the result by Figalli. 1989. Because in some sense is how I think it's instructive. So it's how would you even attack this problem if you have no clue how to attack a problem? What do? You put extra assumptions and you try to solve it in some simpler case. Especially you hope that in some simple situation, whatever, you can prove the sharp inequality, which should be with 1/2. Okay. So what Figalli did, in fact, was to study the case of convex sets. And in particular, the case, so he proved the result for every convex set, but in particular, as part of its proof, he studied sets which are already assumed to be close to the sphere. So Figalli considered the following setup. E is C1 close to B1. It means the following. There exists some function U on the sphere with values in R, U very small, C1 norm less than epsilon, such that I can parameterize its boundary in the following way. So I have my sphere, and then for each directions here, omega, I'm gonna take a segment of length. So this is my boundary of it. Let me first draw it. Should be something very close to the sphere. And this length is U of omega. Is how much I'm off from being in a sphere in each direction. So this means what? It means that I have a function U of the sphere, which is very small, such that the boundary of it can be parameterized as the set of points of the form 1 plus U of omega times omega, where omega is on SR-1. Yes. So the length of this vector, this is 1, and this is U. So 1 plus U is this vector. And this you do it in every direction. So the first, essentially what Figalli did, really, besides analyzing convex sets, was to ask itself, can I prove some inequality like this, at least in this setup? Which would be like close to the sphere. But you see, it's close in a very strong sense. A lot of regularity. Okay. How do you do this? Well, just start to expand and see what happens. So let's do it. You take your energy, F of V, and this is what? Perimeter of V minus perimeter of V1. And you want to write it in terms of U. So to write in terms of U, well, there is a formula, the area formula, just on the sphere. So it's a variant of the area of a graph, but usually probably most of you have seen the formula for the area of a graph where you want a graph on a ren. This is a graph on the sphere. So on a graph on the sphere, you have something like integral over the sphere of 1 plus U to the m minus 1. This is like from polar coordinates. And then you have like an area factor, which is grad U square 1 plus U omega. So this is the area of P. And then you have the perimeter of the unit ball, which is just minus 1. This sphere. Okay. So the first term, when you integrate, you get this. And the minus 1, when you integrate, you get the perimeter of the ball. Okay. now you just take this term and you can Taylor expand it. But before doing that, you have to remember assumptions. So first assumption, the volume of E should be equal to the volume of V1, right? We are considering this. So you can impose this. This is something like the integral of 1 plus U to the n minus 1 over the sphere over n, 1 over n, if you want. This on the sphere is equal to 0. That's another way to write it. And then you can, so you have this and you have this. And you can also Taylor expand this if you want. But if you only use these two information, I can tell you from now, and maybe you could also have guessed that you cannot prove an inequality. So if you try just algebraically to say, I have this information, and I want to prove this information, this inequality, you cannot do it. And there is a reason, which is building to your question, because your set E could just be a ball slightly translated, right? So it could be that I have B1 is my model case, and then my E is simply a ball centered epsilon away from the origin. Okay? And so in this case, if E is just B1, let's say, translated by epsilon in some direction, in this case, that expression will just be 0. Because the E is a ball, so that term will be 0. And by Taylor expanding, I cannot get anything useful, but if I'm expanding 0. At most, I can get something negative, but I will never get something positive out of a term which is 0. And so in some sense, I will never get any stability information. What is the reason is natural, because I'm parameterizing a ball with respect to the Brunn ball. Because if this was already a ball, I should look at it with respect to itself, not with respect to a translated ball. So it's just that I'm forgetting that there are a lot of minimizers. So to avoid this, you can add a third constraint. So if E is as in Sobolev, which means that it's close to the ball, up from small translation, we can assume that the barycenter of E is the origin. So if I have a set which is close to the sphere, I can, before starting this argument, I could first translate it a bit to make sure that this barycenter is at the origin. And now I can start. So in this way, I kill this example. I don't risk that I'm on the wrong ball. Okay, and then this will give me a third constraint, which will tell you something like the integral of 1 plus q to the n times x is equal to 0.
Can you clarify that this first formula is already using the second formula?
No, this first formula is just an identity. It's just a definition. It's just the area of a set minus 1.
It seems to say that if the dimension is odd, then every set has area greater than V1. Because then n minus 1 is even, and then it's, the minus 1 is not in the IC. There's no brackets.
Yeah. No, this is just the area formula. It's just when you parameterize a graph of
This
this
is what the
sphere.
brackets are. Yes, yes, yes.
Then this is the volume constraint, and now I have a barycenter constraint. Okay, and now I can start my Taylor expansion. I will not do all the computation, but it's now really just taking and expanding.
Can you remind us how we can see that the isoperimetric inequality itself is even true in these formulas?
Sorry, okay.
Can you remind us why is f of E always non-negative?
Here you don't see it yet.
Right, exactly.
Yeah, so that's not obvious. So a priori here, this could even be negative, right? But I believe it's true and I'm trying to do something, right? In particular, we prove that it's not negative regardless. So essentially what you do is the following. You say, I take now my f of e, and I start to Taylor expand. I will have, so the first step, there will be a term which has a 1 coming from the first product, but then we'll cancel with a 1. Then I will have a term in u. So there will be something like the integral of some coefficient an times u plus a term in grad u square, which will have constant 1. Then I will get a term in u square, and I can tell you that we'll have minus 1 over, if you just expand, you compute this, n minus 1, sorry, no, another term, let me do it quickly, dn u square, plus higher order terms. So this is what you get. Where higher order terms means cubic terms in either u cube, grad u cube, or higher orders, or products, like u square grad u square u. Okay, now you get something like this. And then you use the volume constraint. So the volume constraint, when you expand it here, you will have something like integral n times the integral of u equal to whatever you get on the left. So it will be like minus n minus 1 over 2 integral of u square plus blah, 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 blah. And these are all higher order terms. When you just, so the first term cancel, right? The 1 cancels with the 1, then you have n times u, and then when you do the binomial expansion, you have u squared, u cube, and so on with coefficients. And this will tell you that nu is equal to this. Now you take this relation and you plug it in here to get rid of the u. So here you keep going and you say grad u squared. So here let me give it a name, star. So if you apply star here, you will have this, less n u squared is over 2 plus higher order terms. Okay?
There's the bn u squared too.
Yeah, the dnu square combined with the n gives
That gives you that.
So I already know what the constant.
Okay.
So this is a constant that one can already guess what it is, because this would be the constant. This expression should be 0, this term, if I was testing on translation of the ball. So if I just took as a function u, the one corresponding to ball slightly translated, this expression will come 0, because that's the part where you have the genus. But now, so you have this, and then you have higher terms. And then the question is, what can I do with this expression? So you have a positive term against a negative term. This looks like, for people familiar, like a Pointer inequality, gradient against function. And then the question is, does this expression has a sign? So in general, for every function u, it will not have a sign. For instance, u equal 1. If you take u equal 1, this is 0, this is negative. But u equal 1 is not really an issue because it will never satisfy this constraint, or u equal epsilon, in fact, u has to be small. So if you look at this thing, so I use this to substitute u, but it also tells me something here. Because now u is bounded by epsilon, this tells me something like the mod of u is bounded by u squared, which is quadratic in u. So it's bounded by epsilon times the norm of u in L2. It's quadratically small because this is norm squared. So if you put just one norm, you can put an epsilon. Right? So this is linear in u, this is quadratic in u, but u is epsilon. So this is epsilon squared. So this tells me that u, the integral of u, it's almost 0. So you should have in mind that the integral of u is very close to 0. It almost has 0 average. And now the extra information is the barycenter. Now if you use the barycenter information, you will get that the integral of u against x is also bounded by epsilon norm of u net. And so what these two information will tell you is that u, it's almost orthogonal to 1. So integral u against 1, you can think of this as 1. It's very small. And here U against X is very small. And once you put these two orthogonality constraints, it turns out that this expression now is nice and coercive. So there is a constant Cn, that this is greater than grad U squared plus U squared. So the Poincare, these terms dominate this. This would be like, if you are not familiar with this, you could think just when you do in Fourier series. This is like when you have a Fourier series, it's like this is like saying the first coefficient of my Fourier series is 0, almost 0. The second coefficient of my Fourier series is almost 0. And then I only have the terms from the third coefficient on. And then when you write the Poincare inequality in the Fourier series, you get a better constant. Because the Fourier coefficients get, the higher the frequencies, the better is the Poincare inequality Fourier series. So the point is that you kill the two enemies, the first two, with these two constraints. And then you have the inequality. And once you're here, you just go on, you say, okay, this now is enough to absorb the terms. And then everything give you that this, so I'm just gonna keep U squared, Cn prime integral U squared. By order inequality, this controls Cn prime integral of U squared. Order that 2 begins in 1. And now look at this. So if I have my set E, if I control the modulus of 1 and then modulus of U and then integrate, you see modulus of U is this length. So if I know, so the modulus of U is this length, and then I'm integrating this over the sphere. When I integrate what I recover is exactly the volume of all of this. So this is really, so I got that f of E is larger than a constant. And then E delta B1 square. The square is here. Outside. Okay. So this is the sharp inequality, but close already in C1 to the sphere. Now you could say, okay, that doesn't look so general. Agree. But I thought it was instructive to see how you do it, at least in C1 sets. And now the next one would be what should I do in the general case? So here is where I will use a black box. Which is optimal transport. So what is optimal transport? Maybe many of you knows it, some never heard of it, I don't know. I just tell you what is the step. So in optimal transport, this is the issue. You have two probability densities, F and G, defined both in a REN, let's say. And what you do, you want to transport one to the other in an optimal way. What does it mean? So first of all, what does it mean to transport? It means that if you give me a set A and you look how much mass G gives to A, this should be the mass, the same mass that F gives to the counter image. Okay, so we say that T sends F to G, so it's a transport, means that the integral over A of G is the same as the integral of F over the counter image. This is just the definition. And then you want it to be optimal. What does it mean? It means that it should minimize some cost, some transportation cost. So the idea is that transporting material from one place to another is expensive, and you want to do it in an efficient way. So I'm going to consider the cost, CXY. So this is the cost from X to Y. And I'm going to take it to be X minus Y squared, quadratic cost. And now with this choice of the cost, there is a beautiful theorem. Let's say 87. And then there has been also, so I will also add a couple of results in it by Caffarelli and McCann in the 90s. That says that given F and G, there exists a unique optima. Okay. So that's the first part. So if you look for a map that transport F to G, minimizing the cost. No, I want to use this just as, I don't want to spend too much time, but there is all a setup, a theory and everything. So essentially the idea is that you pay to move one point of mass. So if you want to move a point from X to T of X, you're going to pay this cost or this cost. And you can do it in a way to minimize the total cost. So there exists a unique optimal T, which minimizes the cost. So the cost is the cost to move one point integrated against all the mass that you transport. And more importantly, this transport map has a structure. So T is the gradient of a function phi, where phi from Rn into R is convex. So the optimal map is not any map, but is the gradient of a convex function. And the third point, the push-forward condition here can be rewritten by saying that the determinant of gradient of T is F over G composed G composed. So these are just facts that I will just put them on the plane. So there exists a map, which is optimal. It's the gradient of a convex function, and it satisfies some P.
How much regularity?
In general, very little. Let's say, but depending on situation, you can do better. But most of the time, there is very little regularity. But you can enough to write the determinant of the gradient, but not much more. So you have one derivative, but not much more in some very reasons. But let's say for now, let me just try to, let's pretend you don't have to care about where it's coming from. The message I want to convey to you is that there exists a map which has some properties, and you will see why these properties are useful in the next 5 minutes, and then I will end for today. But I want to kind of motivate why this is cool. Maybe let me with you. So if you accept that this map exists, we know this method, then let me tell you what you can do with it. Then we'll discuss much more this map on Wednesday. So back to, so we have the isoperimetric inequality, right? That you want to understand. So I have a set E and my unit ball B1. Now I have a theory, optimal transport, that tells me that I can transport probability densities. So I said it in words, but maybe I didn't write it. Integral of F equal integral of G equal to 1. Maybe I should do that. I said it in words, but more at least I do. So I have two sets, E and B1, which have the same volume. So I want to transport them. I want to transport this set onto this set. How can I do that? I just have to associate to these sets probability densities. What does it mean? I'm going to take F to be the indicator function of E normalized by its volume, and G to be the indicator function of B1 normalized by its volume. So I just put constant density here, constant density here. I have two probability density. Then optimal transport tells me there exists a map T equal grad phi that transport this to this. Okay, what can I say about this map? I have three properties of this map. Property 1, the modulus of T of X is less or equal than 1 for every X in it. Let's assume that T is smooth. So if you have a point here, X, this will be mapped somewhere here in T of X. So this point is in the unit ball. So unit ball means modulus less or equal than 1. So this is just because T of X is in the unit ball. Unit ball by definition is modulus less or equal than 1. Property 2, the determinant of the map is there. Determinant of gradient of T is equal to F over G, but F is the constant density 1 over modulus of E, G is the constant density 1 over B1. So you plug it in, you get B1 over E, which is 1 because these two sets have same volume. So this map has determinant 1. Third property, and this I will just, for the moment, just write it. The divergence of T is larger than the determinant of grad T1 over F. Let me just skip this for a second. So just believe it for property 3. And now I want to show you why with these 3 properties. So this is immediate. This is the PDF before, and this I have to prove. But if you accept these 3 inequalities, then what you can do is just the following. You take your set E, again, nu of E denotes my unit normal, and then you just say, okay, what is the perimeter of E? The perimeter of E by definition is the integral over the boundary of E of 1. Now, by property 1, the 1 is larger than the Morse of T. Now, the modulus of a vector is always larger than the scalar product of the vector with the unit normal. Right? So if I take a vector and a scalar product with the unit normal, at most I will get the modulus of the vector. And now this is just the flux of the vector field across the boundary. So by Stokes, this is the divergence. Okay. But by property 3, the divergence of T is larger than n integral V of the determinant of grad T, 1 over n. Then you plug property 2. By property 2, this is just n volume of E of volume of V1. It's the paper. And the other. Okay. So this is a very short proof of the isoperimetric inequality. So I use this black box. I have this inequality, which is really where the optimal transport plays a fundamental role. And for those of you who have heard about it, it's really a arithmetic geometric inequality done in the right way. You will see it somewhere. But I want to keep a bit of suspense. But the message is a bit motivated by one question before. Is like, how do you even see that the isoperimetric inequality is true? So if you want to prove any stability, you should at least have one proof of the inequality itself. So it's difficult to prove something is stable if you don't even know how to prove that the inequality is true. So at least now I have one proof of the inequality. I gave you at least one proof of the inequality that I would like to show to be stable. And so what I would like to do next time on Wednesday will be to discuss this proof, both in particular the role of the optimal transport to get this inequality, show actually how this proof is more robust than one thinks, because it can be used to, for instance, to prove Brunn-Minkowski stability for Brunn-Minkowski inequality, which is also the nice place to discuss it here because it was discovered by McCann when he was a PhD student in Princeton with Elliot Lee in around 95. So it's it's the right place to say it here. And then discuss, you will see that this is just one small part of the picture. And in fact, as you start to delve into this world of inequalities, suddenly these methods break down in most of the other situations, and then you have to start to rely on tools from additive combinatorics, from PDEs, from this and that. And in the next 2 lectures, I will try to move from that. But at least I wanted to show you some elementary approaches. So I stop here for today. Thank you. Questions?
So in this proof of the
Fugalli.
so it seems like you end up with an estimate, you get control over the gradient of unit cell.
Yeah.
So it seems a bit crude to just say that you're controlling the symmetric difference. Can't you say something slightly more precise about the set?
Yes, so if here you say, okay, here I've been just throwing away this term, right? That's what you, fair enough. So so you could go on, you could keep this term, and then instead of controlling only so I told you that this term will control the symmetric difference, right? But then this term, essentially, you can rewrite it in terms of E, and it will control something like this: the interval, the boundary of E, of the normal of E at x minus x over mod x square. So it will control how much the normal oscillates compared to the radial direction, right? So you are on the boundary, you have your point, and so the normal will go here, and you are controlling this angle. The sphere for the sphere, this angle is 0 all the time. So you could calculate the term, and you will get a control on this oscillation of the normal.
Yes. Okay. Thank you.
So in the in the proof of the isoperimetric inequality, kind of the key player of the seems to be that one, right?
Yeah.
Which you don't necessarily need actually to have a mass transportation map, right? I mean, you can even construct other maps that have that property, if I remember correctly.
Yeah, the Knote map.
For instance, can you actually even use the Knote map to get the quantitative version, or will you actually really need there that it is the optimal transport? I mean, when you show us this.
Yes, which I did. So to just prove the inequality here, there are many maps.
Yeah. Yes.
I don't know any map to prove stability after, because at least the only other map that I know for which you have this inequality is the Knote map, which is a map which there are infinitely many of them.
Yes.
Because it depends on the system of coordinates.
Yes.
And so
I mean, that one
you
doesn't
could try to say
you average for this. You average, for instance, on the system of coordinates.
you could try to do stability with each of them and then try to average. Let's say when we tried 15 years ago with the, we couldn't do with the before doing Optian transfer, we were really trying with Knote because we didn't for understanding, and we always had problems because of this. What if your set look okay? Fair enough. See, one thing which is interesting about this proof is that it doesn't matter that you're using the isoperimetric inequality or you do the Wolf inequality. So the proof works also if you change the perimeter with a different perimeter given from a different norm, not exactly the Euclidean norm. And then the proof will go through without problems. And so when we were thinking about this, we were in mind the Wolf inequality, right? And in that case, if you use the Knote map, maybe your sphere and your geometry, it's a square, for instance. And then the Knote map you took is a bit tilted with respect to the square. And then it looked to us like you had to choose the Knote map depending on the geometry of the Wolf itself, which didn't look very promising. So the fact that otherwise we had always this system of coordinates that was fighting with the geometry whenever the faces were very sharp. So maybe on the sphere there is a chance. It's true that we never tried on the ball itself. We were already working on this with the Wolf. But it's not so obvious to me because we are, also the regularity is not the same, right? I mean, it's, you don't have the nice properties of the Austrian transform map.
Are there other cost functionals that you could use to get these kind of results? Are they always quadratic?
Well, no. So you see, okay, let's say all the results that we use mostly on a REN. So when we work on a REN, we want to prove isoperimetric, Gaussian inequalities, Sobolev inequalities, you always use quadratic. But for instance, if you want to use, to prove, for instance, some Levi-Gromov inequality, which is on the sphere, or any isoperimetric inequality on the sphere, for instance, which there are no proof with optical transport. It was realized by Klartag about 10 years ago that you could use the cost distance equal power one, the power one cost. And this is a way, the power one cost is a bit special because it doesn't, instead of doing this, giving you this map, it allows you to reduce an n-dimensional transport problem into a family of one-dimensional problems. So essentially you do transport along curves, geodesic curves. And what Klartag realized that this is totally connected with the Gromov needle decomposition, where in some sense when you have a geometric problem, you can decompose your n-dimensional space in needles, which are one-dimensional objects, and reduce your n-dimensional inequality to proving a family of one-dimensional inequality on these needles. And let's say the Coera factor, it what creates a weight on these needles. So there is this dimensional reduction. And so Klartag understood that optical transport was a very efficient way to do this needle decomposition that then was used to prove Lemmy-Gromov inequalities stability also, and also on metric spaces, for instance, using optical transport. So sometimes the power one actually works very, very well when the quadratic doesn't work, and vice versa. I don't have a case where both work. So usually it's either one or the other or not, and then you just doesn't work. Yeah.
So the example that you gave with tentacles outside.
Yeah.
So is it very different if you try to do tentacles inside?
Oh no, it's identical, right?
Okay.
So there is no in the supermetric inequality, it doesn't matter.
But you don't see it in any type of construction like this, right? I mean, it's symmetric.
So for the inequality in those these, I don't see a difference. Now, once I will explain a bit the proof of the stability, for our proof, the tentacle inside is different from the tentacle outside.
I see.
So it helps in the stability if there is a direction, but that's maybe an artifact also of the proof. But it's true that, well, there is not, I don't think it's an artifact, right? So if you try to transport, let's say if I try to transport a set with a tentacle outside to this, or a set which with a hole inside is not totally, is not really equal, right? So this tentacle has less effect than one, because here I have points very far away that are mapped here, and here instead I will have just a small collapse of this tentacle. So the geometry of the transport map is actually much nicer here than here, but it's just because we use optical transport. I don't know, I mean, geometry, I don't see a difference, right, from these two pictures. But for the point of transport map, inside is better than outside.
Well, there is a limit of how much you can actually like get it going inside versus outside.
Right, but let's say if I even just do small tentacles of length 1/2, but very tiny. So from the local picture, I don't see a difference, right, inside and outside. But the global picture comes from optical transport, and there it makes a difference. But let's say from the perimeter point of view, it should be similar.
So once you're writing this effect setting with a T, how can you tell the center of mass? How does it come in anymore? Once you have the picture in the abstract setting.
No, in the abstract setting you don't see it, right? But then you always take the minimum with respect to the manifold of minimizers, this M.
And how do you know the minimum is when the center of mass coincides?
You don't know that the minimum is that, but you can prove that the two quantities are equivalent. So once you know that you are close to one of the minimizer, then necessarily barycenter is going to be close. And then if you just shift the barycenter, so the inequality is like this, right? So suppose, maybe let me erase this anyhow. So suppose that I can prove, let's say that f of e to the alpha controls the distance between E and the manifolds, right? So E and B1 of X for some X. So I have an inequality of this form for some X. So this is the symmetry, right? I think it's the delta B1 of X. Then this quantity controls the distance between the barycenter of E and the barycenter of X, which is X itself. So if I control this, I also control this. But then it means that I can always now shift. So I could now take, let me call this barycenter X bar. And then I have that E delta B1 X bar is bounded by E delta B1 of X by triangle inequality plus B1 of X minus B1 delta B1 X bar. And now this term is controlled by this. And this term also is just the difference between the center of two balls. And this goes like this. So this goes like X minus X bar that I control again by this. So up to doubling the constant, let's say, by triangle inequality, I can always replace. So I'm not saying the minimum is at the barycenter, but let's say up to constant is the same to control one of the other.
Okay, maybe we have a questions. So thank you.